Good afternoon, faculty and students. My name is Jorge Salazar. This is our Nair Tariqa, our project manager, Mohammed Irfan, and Shiraz Khan. And today we're going to present to you our quick surface thermal scanning system. Diabetes. An estimated 171 million people worldwide suffer from diabetes. By 2025, they expect this number to reach 366 million. Now, diabetes can affect various body parts in various ways. For example, nerve damage in the lower extremities, which results in loss of sensitivity. Due to this loss of sensitivity, patients are unable to detect pain, making them 10 times more likely to suffer from a foot ulcer. Now, a foot ulcer is an open sore which can extend to the full thickness of the skin. Among people with diabetes, it's very difficult for them to heal from an ulcer, and which makes them heal from an ulcer, which even a small ulcer runs the potential of getting infected. Now, studies among National Institute of Health have approximately 85% of severe infection cases actually result in some part of the lower extremity of the patient to be amputated. Now, recent clinical studies have shown that detecting a 2.2 degrees Celsius increase among day-to-day trends is actually an early sign of inflammation. With proper foot care or foot monitoring, one can lower the chances of this inflammation actually developing into an ulcer. So, before we started the design phase, we looked at all the available products on the market today. What we wanted to do, we wanted to incorporate all their pros into our design and also make up for where the downfalls were. And at the end, we decided that we need these key features to it. We wanted to develop a system which was low cost. We wanted a system that had data logging capability, and we wanted a system that had a high sampling rate. Now, the question at hand is what would be appropriate sampling rate for to detect the spatial variation in temperature among the human feet? So what we did is that we got our hands on a high-end infrared camera, which had excellent resolution and excellent thermal sensitivity. And what we did, we essentially took several samples of students' feet, and we took these samples and we pretty much viewed them as signals, in which now, instead of viewing to view the actual spatial variation between temperature among each pixel, instead of viewing them as distance, we viewed them as time. This enabled us to form a discrete Fourier transform to see what's the required sampling rate needed to detect the spatial variation in temperature. And after all their cases, we determined that our sampling rate needed to be 0.9 centimeters, which was our worst case. Now, we do understand that we didn't actually try this on a real diabetic patient, but we realized that as of today, if a diabetic patient would use any of the automated devices available on the market today, they're looking at about 11 samples per feet. Now, if they incorporate our design, a men's size 12 foot would get approximately almost 400 readings. Now, I'll pass it off to Nair to talk about the requirements of that.
All right, so our requirements. With our requirements in this project, we work with a company named Polo. Polo is a leader and specializes in remote monitoring systems. From our requirements, we wanted to have a weight scale like device where the user could stand comfortably and take measurements. So this device had to be self-administrable. It also needed to be fully automated and had to have capabilities of sending data on a text format. Also, it must be compact and low maintenance. Moving on to our specs. For our specs, as George mentioned before, we had to have our spatial resolution of 0.9 centimeters. Also, our thermal sensitivity had to be 2.2 degrees Celsius or better. It had to be 2.2. Our system had to be able to detect 2.2 degrees Celsius among adjacent cells. Okay? So, in our procedure, this whole procedure, by the way, had to take place in less than 30 seconds. Furthermore, our platform would have to withstand a tremendous amount of weight, so we estimate about 300 pounds, at least 300 pounds, and should accommodate for foot size, men's foot size. Okay. Our approach. So we approached this problem knowing that we had a spatial resolution of 0.9 centimeters, so we needed each sensor to be 0.9 centimeters apart from each other. So we decided to go with thermistors. What a thermistor is? A thermistor is a sensor that changes in resistance with the increase in temperature. So So we chose thermistors because of several reasons. They are accurate, precise, and they have it they're linear in the human body range. Also, the size and the cost. Well, there's a little problem with thermistors. A thermistor basically is a resistor, so when voltage is input into it, current goes through it, and it causes heat. So in our design, we had to accommodate for self-heating. All right, our system architecture. Our system architecture consists of our temperature sensing, where we get our multiple analog readings, which later on go to our signal multiplexing, which then are processed by our data conversion. And from our data conversion, go on to our data logging. From our data logging, it goes through our data interpretation, which is full display. Now I'd like to pass it on to Mohammed to explain this in detail.
I'll try to walk you through the details of our system. So let's start by looking into how each function is achieved or implemented. For temperature sensing, we use thermistors as our sensor on ABS plastic platform. And then the signals that we get will go through a signal multiplexing process, which will perform the multiplexing from the many sensors that we have. Those selected signals will go to our microcontroller to be converted. So the raw reading will be converted into the final data, which we know is temperature. Finally, those temperature values will be saved into a text file using a software called processing on our PC. And we get the final product, which is temperature data in text file. Let's look into more details, a little bit more for each function. So for the temperature sensing circuit, we use ABS plastic to build our platform for strength. And we can build it using a 3D printer, which gives us precision on spacing. So we can satisfy and fulfill the spacing or sampling requirement. And you might be wondering, how can we get temperature from thermistor? So we use thermistor resistor voltage divider circuit. What it does is, the thermistor essentially is a resistor that changes with temperature. So when the resistance of the thermistor change, the voltage across the resistor also change. And we take that reading. We choose to take the reading from the resistor because it's more stable. We can get a better data acquisition method. And we are using 1.1 reference voltage to avoid self-heating, like it stated before. There is a problem with the thermistor which is self-heating. So doing some calculation, we come up with 1.1 reference voltage, and we can avoid self-heating. So the data that we get from the temperature sensing circuit will go to our multiplexers on the PCB. Because we have close to 400 sensors, we have to scan through each thermistor to get the data and then pass it on to the analog to digital converter to be converted into temperature. So we use 32 to 1 multiplexers, analog multiplexers in cascade, and control them using digital pins on Arduino Uno. Finally, those selected signals will go through data conversion process, which will then by an ADC or analog to digital converter capability of our microcontroller. And we use the ADC value will be converted in temperature value using Steinhart-Hart equation. So now we get our temperature values. Those values will be saved in the text file using a processing software. And we choose a text file format as stated before, so it's easy to transmit into a network and easy to analyze. And our processing software has a graphical user interface, which allows them to start the reading and then interpret the data. And now we would like to show you how our system works.
as risky as this is, we're going to be doing a liability. Here we have our platform. We got a power switch and reset for the microcontroller.
Hold it up a little bit so it's set where it is.
Here's the platform made out of ABS. We have the power switch, the reset for the microcontroller. We have all the sensors on the top and a heel cup to help guide the feet.
There we go.
And now we're going to run our software. This is our GUI. We got start, reset, or restart and exit. And he's going to put his hand on the platform as we run it. The stabilizing thermistors, we'll go into more of that in the testing. But it's required because then you know how long you have to wait in order to get stable reading. Okay, right here it just saved the data. We have our results. We have it by lux, thermistor, analog reading, resistance value, and temperature value. And as you can see where it's increasing where he put his hand. And we're also going to show you, since we know the order of our sensors, and we have it in this text format, we're able to do some imaging in MATLAB. And we're going to show you a grayscale image of his hand. Right here you can see the pinky, the index, middle finger, ring finger, and thumb. These black spots are thermistors that weren't functioning. Out of 400 sensors, we have about 10 or so sensors that for some reason short circuit or they're just malfunctioning. Once we had our system fully integrated and working, the first thing we did was we got the step response of the system. We did this by introducing a change in temperature to a single thermistor and sampling it at a higher rate. Once we got the step response, we looked at where the temperature reaches a settling area, and we took 5% of that value, and we were able to come up with a stabilizing period of 20 seconds before you take the readings. And then what this helps us do is it lets us know how long our entire procedure is going to take, because down here we have the switching time of the muxes, which is in the order of nanoseconds, and the microcontroller, which is microseconds. We can just say that's 1 second for now. For settling time, we have 20 seconds, and then the read and write time, when it's logging the data, it's 4 seconds, which gives us a total of 25 seconds for the entire procedure. Once we had that, we did the thermal sensitivity on our device, and for the testing, we did, we heat up a water bag up to a human temperature range, and then we place it on the platform. We sample it every 10 seconds, and we wanted to do this to see the smallest differences in temperature our system can detect. In our actual data, you can see that it's about 0.1 plus or minus 0.01. In our theoretical calculations, what we did was we plugged in two arbitrary analog readings of 499 and 500, and then we got two temperature readings down here, 25.1854 and 25.0979, subtracted 2, and that gave us a sensitivity of 0.0875. So the difference could be rounding, or since that's only up to 100th place, we did it in a more theoretical sense. And then the third testing we did was reproducibility. We wanted to see if every day you measured the same way and there was no change in temperature, it would give you the same results. It was really difficult to have a closed environment that would provide us this. So for the trials, we stuck with indoor testing and ambient temperature. And as you can see, the environment temperature range, that was from our infrared temperature sensor. So we can have something to compare our results with. And then we have the mean and standard deviation of each thermistor. And in each trial, we ran through every single sensor one time. And as you can see, throughout the trials, it's approximately equal every time. And these are our project costs, man hours down here, and total cost with the approximated $30 an hour. are the major contributions to the project. Nair was responsible for the AutoCAD design of the PC platform. Mohammed was responsible for the PCB design. George did the spatial resolution, and I did the microcontroller coding and processing. For future improvements, we would have completed the other side, so you should do both at one time. We would have picked different thermistors because the ones we got when we pre-sampled them, you can't really tell the difference in size. We got 500 of them, and then it was crazy. Like, everything was different sizes, and we had to accommodate for that in our platform. And then we do have a heel cup for foot alignment, but in order to make analysis easier, we would need something that's more precise. And essentially what we did with this project is we designed a prototype for Trapolo, which is the company we're working with. And currently we have a patent pending on our device. Now I'm going to pass it up to Nair to close out the presentation.
All right. So what are the lessons that we learned? We learned several key lessons. One of them was be prepared. Be prepared to move on from plan B, plan C, and perhaps plan D. Also, they tell us every time at the beginning of the semester, allocate extra time for system integration and testing. True, please do. Also, anticipate to learn something new, hard, and keep in mind, you will be on your own. Now, our special thanks and acknowledgement. First of all, we would like to acknowledge and give a special thanks to Paul, to Mr. Todd Ligo, John Aldridge, and Peter Bonanno. Also, our faculty advisor, Dr. Pancrazio, was great throughout the semester, gave us so much valuable feedback, along with Dr. Vicky and Dr. Jim Chen. We all thank them for allowing us to use the rapid prototyping 3D printer. And of course, our family friends, big thank you. Thanks for coming.